Now, if there's a net charge density, Gauss's law tells us that net charge density requires some finagling of the electric field. In particular, the divergence of the electric field has to be equal, or the local divergence of an electric field has to be equal to the net charge density divided by the what's called the permittivity of the medium. And so the permittivity of a vacuum is a well-known universal constant. It's equal to 8.85 farads per meter, 8.85 e to the minus 12 farads per meter. And then we define something called the relative permittivity that depends on what the medium is. So by definition, it's 1 in a vacuum, but it's generally a number higher than that. And for example, in water, it's as high as 80, which is pretty high. And in some solids, it gets up into the several hundreds. So if I kind of put that together, so let's take Gauss's law and write it out, using what we know about, the net charge. So that would be the sum of the number density of all of the ion species that I have run around times the elemental charge per ion, and then I'll pull out the fundamental charge E, which is equal to 1.6 e to the minus 18, or sorry, no, that's not correct. It's e to the minus 19 coulombs is the fundamental charge. All right, so what I can do is recognize that the electric field in turn can be written in terms of an electrostatic potential. So the electric field is minus the gradient of the potential. And in that case, I can replace the divergence of electric field with the Laplacian of the electric potential, keeping the same right-hand side but changing it to a negative sign. So what I want to think about now is what exactly should the potential or the voltage field, what should that electrostatic potential look like inside the liquid? So what you have to think about is, well, what does the charge imbalance look like? So in the example that I had drawn before, there was a net negative charge inside the liquid that had built up near the surface. Now, obviously, like very far away from the surface, the Laplacian of the potential must be 0 because there is no net imbalance, and that means that the electrostatic potential is basically flat. Generally, we define the electrostatic potential in the bulk to be equal to 0, and then we measure everything relative to that. So you've got a center where there's charge neutrality and the electrostatic potential is 0, and then as you move closer and closer to the wall, there's more and more net charge. So in the example I had given where there was a slight net negative charge, you would get a slight curvature then to the electrostatic potential, and as you move closer, you would get an even more rapid change in the electrostatic potential. So basically, you have a voltage rise near that surface is what you're expecting to see if there's a net negative charge buildup near the surface. We can do a little bit more than that, though. We can say something about what the number density of ions is at a particular point in the fluid by sort of thinking about statistical thermodynamics. So what we know is that the probability of essentially the probability of the number density of ions being a certain amount is proportional to a scaling factor that is basically the chemical potential divided by by kBT, the thermal excitation energy. But in fact, we can figure out what that constant of proportionality is by just looking at the place where that chemical potential is 0. So when the potential is 0, that happens to occur when we're in the bulk of the fluid, and so I'll just define the number density of the bulk of the fluid as the prefactor, and everything works out nicely. All right, so let's put that all together. So if we go back to our Gauss's law and sort of put it all together, we get that the Laplacian of the electrostatic potential is balanced by this net charge from place to place, which we now know is related from statistical thermodynamics by an exponential factor that itself has the electrostatic potential tucked into it. Now, the problem with that is that what we're trying to do is solve for the electrostatic potential. That's what we would typically want to do. And the problem is that the electrostatic potential doesn't show up as in a linear way in these equations. So in general, that's going to cause some problems. Before I address those problems, let's try to assign the boundary conditions for this case.